Again, good morning and welcome to Physical Science. Today is week 5. It's a very, very important week. So you guys really need to be on top of things because we have an exam that is coming on this week. So we really have to prepare for it and make sure that we're ready for it. I know we have a review on Canvas, and that review is actually graded. So and it's graded for participation. For those who took it, and there are a few who took it so far, they received full credit for their work. So in a sense that even if you don't score 100% in the review, you still get 100% grade for it. So it's really something that you really should do for 2 reasons. First of all, to make sure you receive the credit for it, because you're going to get full credit. That is a good enough reason, I think, to do it. Okay. Otherwise, you're not going to get any credit. As a matter of fact, you're going to lose points. So it's not like if you don't take it, nothing happens. Actually, you're going to lose points. So it's very important to do the review. Excuse me 1 second. So the review is very important for this class. For all of the exams, you will have reviews, and takes about 2 to 4 hours basically to do the review, depending, especially if you don't have the book, you might need to do more digging and more research to find the necessary resources for it. Other than that, that's basically the time it takes. The review has a lot of questions in it, and the exam is actually a lot shorter than that. So the review is going to close on Wednesday night. So if you don't do it by then, 2 things will happen. The review will close and you'll receive a 0 mark on your review attempt because you did not take it. If you take it by then, you will receive the full mark for it. So it's very important that you guys are there. Let me share with you the screen. Let me first of all change to the view from the vantage point of the student so that we see exactly how it looks like to you. So if there is a problem, at least we can address it. So let me share screen. So this is this week's objectives, of course. Let me look at them again. As I was talking about, this is the review, okay? The review is essential. It's a participation grade. So you get full credit. It's 246 points. You'll get all of the 246 points if you take it. If you don't take it, you get nothing. Those are the only 2 grades you're going to receive for the review. Either a 0 or 246. Please do not be alarmed if Canvas will give you a grade in between. You get, for example, 135, for example, points. Okay? Don't worry. I override Canvas. Okay, in this case, you will still get the full credit for it. As a matter of fact, for those who took it already, there are quite a few who did, they already received their full credit for participation. So this is an easy grade to get. All you have to do is open this thing, and even if you get them all wrong, you still get full credit. The point in here I'm trying to encourage you is to actually spend the time to go through all of the 4 weeks, basically, materials. Week 5 is not included in the exam, by the way. What we do today, what we do this week is not included in this exam. It's going to be included in the next exam, though. So it's not something that we have to ignore. So that is how this thing is working. The exam is going to open up on Thursday, though, Thursday morning, and you will have a chance to complete it by Monday. And so this is the thing that we have this week. Any questions about this thing in here? For the few who are here. Those who are not here, they can watch this recording later and hopefully they will get the message. I will follow up this with a message, individual separate message, basically it's coming to each and every one of you guys. So you will see a repetition of what I'm talking about here. So this is concerning the exam and the exam review. Now the content for this week is about fluid dynamics. And fluid dynamics is a little bit in a different context, okay? Again, let me zoom out. Let me come back home in here so that to see what's in this module. And it's not different than what happened before in the previous weeks. Again, we have a review week 4. This is we've been doing it, the concepts that were covered in week 4. And the PowerPoints, which is the summary of week 5, which is the fluid dynamics, what we're covering today. I'm sorry, the summary is here. And actually, this is the video recording of today that is going to introduce the entire week for you guys, and also the concepts covered for this week, and also the concepts from the any kind of practical questions and things like that. I really don't like when we have exams, honestly, to do other things. I don't like to discuss homework problems. I don't like to discuss quizzes or anything like that, because the focus is on the exams. The exams are worth 60 points. So I really want to make sure that you guys are focused on the review plus the exam itself. It does not mean that we're not going to be doing homework from this unit or from this week. It does not mean that we're not going to be quizzed from this week, but not today, not this week at least. Okay? Not this week, maybe next week. Once we're done with this exam and we have it behind us, then we're going to come back to this one in here. Okay? So that's why this unit is this week, basically 5 is structured in this fashion. So hopefully you guys don't have any problems with this one. Okay, in terms of the concepts that are covered for this week, let me put it in context, and we probably are going to repeat this one in the review down the road. When we do week 6, we're going to come back to week 5 and talk about what happened in week 5 and so on and so forth. Excuse me. So far, the main thing we learned actually are Newton's laws. And Newton's laws, which are going to be tested, by the way, they dealt with the law where we have an object is under no net forces. So I have one object under no net forces. 2 conditions. One object, and then what is the story with the net forces? Well, they cancel out. So this is the scenario we're in. Then in this case, the first law says, if that object was at rest, it's going to stay at rest. If that object was moving, it's going to continue moving in the same direction with the same speed. This is the first law of Newton. The second law basically took the same object, and when we tallied the forces, we found that the forces do not cancel out. So we have an object in net forces, A net forces. 5 Newton, 3 Newton, 10 Newton, it doesn't matter, any number, throw in anything that you want, a number. Then in this case, the object state of motion will change. It will accelerate. So it's not going to continue with the same speed anymore. It's not going to stay at rest anymore. It's going to change its velocity. And the rate at which the velocity changes, which is called the acceleration, is proportional to the net forces, but depends also on the inertia of the object. Some objects are much easier to change their state of motion than others. Some objects with less mass, they're easier to accelerate if they are not, if they're moving slower, or decelerate if they're moving too fast, or bring them to stop altogether, or move them because they have less mass. Objects that have more mass, they tend to resist more to the change in motion. Objects that have higher masses, like a big truck or a big train or a big mountain or a big whatever, usually is difficult. You need a lot of force to change its state of motion. Okay? That is really the idea behind the second law of Newton. The third law of Newton is slightly different. the third law of Newton, we are no longer dealing with a single object anymore. We have more than one object, like two objects. See how the baby steps in physics are? We start with one object and qualify that for object in all kinds of scenarios. And there are only two possibilities. Is that object under net forces or under no net forces? We exhausted that single object story. Now we want to explore the rest of the universe where we have more than a single object. We could have a billion of them or trillion of them, it doesn't matter. But we don't do it that way. We go to, after we exhaust the one object, we go to the two object scenario and see what happened in the two object scenario. Because we can't really handle 17 objects at the times when we did not handle 16 yet. So we need to ask what happened to the 16 objects. Once we know what happened to the 16 objects, we hope to have a way of getting into the story of the 17 objects. That's how you solve problems. So this is a skill that was developed by physicists, later on borrowed by other fields on how to do real world problem solving. So if you work in the industry, it doesn't matter. If you are in the medical field and you have a big issue, you cannot tackle it at once. You really try to make it into smaller components, models that is, and fix this one and fix that one and fix the other one. And hopefully the whole thing gets fixed at once, depending on the urgency of the matter, of course. But that's really how things are done. If you work in the IT field, for example, and you have a major project, usually that's what you do too. You don't tackle the whole thing at once. Again, it's borrowed from physics. It doesn't matter if you have, I don't know, an issue, for example, with that you're facing in life. Again, try to break down the problem into smaller components and fix them one at a time until all of a sudden the whole thing gets fixed. This is a skill that was developed in physics, later on used in every other fields in life, including engineering, including non-engineering fields, STEM or non-STEM fields, including whatever you have. So this is a problem-solving skill. Okay, so let me go back to the story. Now, we exhausted the one object, under net forces or under no net forces. Solved that one completely. Either the first law or the second law give you the answer. Now we want to understand what happened to more than a single object. For that, we examine the two object scenario and ask the following question. Are these two objects interacting or not interacting? If they are not interacting, each one of them is a single object and can be resolved in the first law or the second law, depending if the net forces are zero or not zero. We answer the question. If they are interacting, though, the third law needs to be invoked. The third law says if two objects interact, they do so in such a way, if one exerts a force on the second exerts a force that is equal in magnitude but opposite in direction. That's basically how you handle interacting objects. The third law is needed. Now, what happens if you have more than three objects, three objects, for example? Then in this case, you pair them, that's it. So all you need is just these three laws, really. You pair them, meaning you take out of the three, you take two, resolve those two, then whatever happens, then you pair them with the third one and so on and so forth. And you can go about all the way to the 17th object if you like, or a billion or trillion of them, it doesn't matter. So this is basically the state of affairs. An object, usually we mean by it a solid object, like a car, like a ball, like a rock, okay? Those are the objects that we've been dealing with so far. Of course, we ask the question, the force changes motion. That was the second law of motion. How does the force do it? It does it in two different ways. First of all, by changing the kinetic energy by doing work. That's one way, the kinetic energy work theorem, which allowed us to explore further studies, or by imparting an impulse to the object in such a way that that impulse is equal to the change in momentum. So these are the two ways the force does it, either in time or in space, in time by the impulse or space by work. So that's what allowed it to move past Newton's laws of motion. We took practical examples with the projectile motion and different studies that we did up to this point. This is exam one. So what I'm describing right now, up to this point, it's exam one. Now, there is a peculiar kind of objects that cannot easily be described or cannot be clearly described by this object. And case in point, what I've been sipping so far is a liquid. Okay, water. When I say liquid, usually I talk about water. Okay, water, I mean, I can change its motion, but it has this motion inside. Okay, and all of it sits neatly inside this cup. Okay, so I want to describe this type of physics, if you wish. I want to describe the physics of these objects. So let me stop sharing the screen and share with you my notes so that we can have a pen and start writing, okay? So let me add, first of all, a new entry and call it week 5. And share my notes. So basically, the discussion item up to this point is do the review before Wednesday night. So this is, again, some of you come back later on and ask me, I looked at the video, I watched the whole video, and I didn't find where the prompt for today was. Well, right now it's 11:26 according to my time, which means that we started about 16 minutes ago. Item 1 of the discussion is do the review. Make sense so far?
Yes.
For those. Okay, very good. Okay. So we might have another item down the road, so don't leave yet. So if you're watching this recorded later on, you reach the 16th point and you say, oh, wait a minute, he mentioned the review, so I'm going to leave. No, okay, the item of discussion today. For the person who just joined us, you probably need to watch the beginning anyway, the first 16 minutes, but the first item of the review is, the first item of discussion is do the review. Okay, so I'm sharing the screen in here to talk about the situation I was describing, the cup of water that I have been describing, and we want to come up with the physics for it. We want to understand it, in other words, okay? So here is a cup of water. Okay, it's not really a cup of water, so it's a weird geometry, what I'm trying to draw, cup of water. So this is water, okay? In a cup, albeit not a clean cup, but it's a cup nonetheless, okay? I want to describe this water, and I want to have a physics to describe it. If I bring water, for example, and I bring another similar cup, hopefully similar enough, and put the same level as the first one, or the same volume, I should say, volume, doesn't matter. If this is 1 liter, this is also 1 liter, okay? But instead of water, I'm going to put oil. It's still liquid. This is water. How am I going to differentiate the two? Obviously, the color is one of them, but the color is not something that I'm going to carry with me all the time. As a matter of fact, all I need to do is probably add the food color into the water. It's going to look exactly like the oil, okay? So it's still not good enough. So the color is probably one thing. The smell probably is another thing, but all I have to do is probably put some sort of a perfume in there or some product in there, and I'm going to produce also the similar thing. There is actually another property. Weigh this one, how much mass? And mass this one, and compare the ratio of the mass to the volume. Mass over volume is what I call density. Mass is related to how much stuff you have, how much stuff. The more stuff you have, the more mass you have. Okay, the volume also is related to how much stuff you have. If the liquid is not compressible, and you're not compressing it actually, if you double the volume, instead of 1 liter, you put 2 liters. Then the mass, whatever it was before, is going to double. That's it. So if you double this too doubles in the same time. If you double the mass, the volume doubles. This number stays the same, does not change. This is actually a useful property. The density is a very useful property because it doesn't matter how much I bring. I'm using the wrong mouse. I'm sorry. Here is the mouse. I need to get this mouse out of the way because it's confusing. So the water has specific density, does not change as long as I don't change its concentration of the, I mean, I'm talking about pure water, of course, okay? If you add salts in it, obviously it's going to weigh differently. Same thing with the oil, it has specific density. So they are different densities. So the density of water, it's a useful number to remember. Water density is 1 kilogram per liter. I mean, everybody can remember 1. Kilogram is a kilogram. A liter is a typical number that we use a lot, okay? Bottles of water usually is about 1 liter. I know in the non-metric system we use a different unit for it, but it's still about 1 liter. So 1 kilogram per liter. We don't really use the 1 kilogram. For the density, we typically use the kilogram per cubic meter. So if it's a cubic meter, it's 1,000 kilogram per cubic meter. That means, what is that meter? I don't have my meter stick. That means if I am in, open up, basically, if you step up and you put one big step, okay, put one leg one side and try to put step on the other side. That is 1 meter, slightly over a yard. Think of that distance, which is probably this distance. Let me bring my other hand in here. It's about this distance probably. That is about 1 meter. This one is 1 meter, and the depth also is a 1 meter. 1 meter. That is about the weight of a car. Slightly less than a weight of a car. Okay. At least an engine and transmission. So it's about 1,000 kilograms. That is in water. So water has a very high density, relatively speaking. Of course, it's not high enough compared to iron. Iron is 7,800 kilograms per cubic meter. So iron is much more denser than water. Iron, if you put in iron, is going to sink inside the water because of its high density. If you put the oil is less than that of the density of the water, and that's why it does not sink. It stays like on the surface. Okay. So this is basically a property, useful property, and a useful number to remember. There is another unit actually sometimes you hear people use, and it's not actually. So this is the SI unit. But in science, people, they don't use this unit because it's much easier to remember. 1 gram per cubic centimeter. It's the same numbers, all of them. 1 kilogram is 1,000 grams, and 1 liter is 1,000 cubic centimeters. So the 1,000 cancels the 1,000, the number is the same. Okay, so this is for the water. It's a very useful number to remember. Either 1 kilogram per liter, or 1 gram per cubic centimeters, or 1,000 kilograms, or a ton per cubic meter. It's the same thing. When I say a ton, I mean the metric ton. I know that there is the non-metric ton, but that's another story in here. Okay, so that is really the ton is 1,000 kilograms. So but this is a useful property. I can describe the gases with. There is another useful property that can describe the state of the liquid, and that is the pressure. And let me explain what the pressure first of all is. And then we will talk about it in the context of the fluid dynamics. So the pressure, first of all, if you take a force, F, and apply it over this area, A. So you take a pressure, let's say, for example, 10 Newton. I'm going to apply 10 Newton like this. And then I can push my hand with it, but it's there, okay? What is 10 Newton, you're asking? 10 Newton is 1 kilogram apple. Take an apple and put it in your hand. This is actually less than 1 kilogram. No, not 1 apple. Did I say 1 apple? About 10 apples, about 7, 8 apples. That's 1 kilogram, okay? I'm trying to think of a kilogram in here. So it's about 7, 8 apples. Put them in your hand. That is basically the force that you're going to feel, okay? So that is fine. That is one way of describing a force as it affects the hand. However, I can take the same 10 Newton. So this is 10 Newton. That's all I can afford. I have 7 apples, for example, or 8 apples, which is about 10 Newton. 10 Newton? 10 Newton is 1. Yeah, that's correct. Okay. That is correct. It's 1 kilogram times 10, so it's the same thing. So let's say, for example, that's all I can experiment with. But instead of putting them on my hand, I'm going to put them in a container, and the container will have a sharp edge at the bottom. So instead of applying it with this depth, I'm going to apply it like this, okay? It's the same 10 Newton at smaller area. At smaller area, this much area. But it's still the same force, the 10 Newton that I applied before on a smaller area. And if I make this area a lot smaller, like a needle, obviously it's going to have more impact. It's going to puncture the surface. So there is a property in here with the same force, with different areas, things change. So the area and the force combination is a new concept. And that concept is the pressure. New concept. And because of this effects, the effects of this force in here. So if I take, for example, a big block, for example, 1 kilogram, and drop it on the floor, okay? That's fine, it's going to make a dent. But if I make it into a sharp, edgy thing, okay, with a sharp, pointy edge, and it's still the same 1 kilogram, and drop it, it's going to have more dent, more, basically, it's going to leave a deeper mark than if it has wider area. So the area plays a role, the combination of the force area. Obviously, I can make it as pointy as possible, but if I push it with a small force, it's not going to make a difference. It's not going to make a lot of difference. So you need to have a combination force area to make this concept come true. And this concept is a concept of pressure. So the pressure, by definition, is the force over area. And the force over area has a specific units. Well, I know the force has units of, so the units, the force is in Newton, the area is in square meter. So how many newtons per square meter? That is basically the proper unit for the pressure. Sometimes people use, not sometimes, always, we use a Pascal. As a matter of fact, 1 Pascal, so this is called a Pascal. So a Pascal is a Newton per square meter. But because of the latter part of this unit, that you will see that the air also has pressure in it. And when we measured the air pressure, we found it to be the air pressure to be about 101,300 pascals. It's a huge number, okay? So this is the normal air pressure. We don't use the air pressure that much. We don't use Pascal that much in the day-to-day business. We use the atmospheric pressure, the ATM. 1 ATM, 1 atmospheric pressure, this is called atmospheric pressure, is exactly this number. Okay. So when I say 1 ATM, I don't really mean a small pressure. It's a huge pressure. It's 101,000 pascals. That means it's a big number. For every square meter, I have 101,000 newtons applied. It's a lot of force. Or 10,000 kilograms. Think of how many trucks loaded of apples on my shoulders. That is basically the pressure that we see on a day-to-day experience. There is another pressure that you will hear the weathermen talk about it, and the weathermen use the bar. This is for weather. It's the same thing. Weather, W-E-A, okay? They use the bar, sometimes the millibar. So they say the pressure is 101 millibar. 1,113 millibar, okay? And a milli is a fraction of a bar. So this is millibar. And to get the numbers correct, 1 bar is 100,000 Pascal. So a bar is very close for an ATM. So when atmospheric pressure is 1.01 bar. So, but they don't use the bar, they use usually the millibar. So the weatherman usually uses the millibar and tells you that the pressure today, for example, is 1,113 millibar or 970 millibar. That's low pressure. Okay, very low pressure. Or 980 millibar. So it's still a low pressure. So depending on the day, depending on the temperature. So the weatherman uses the millibar. They use actually another unit called the mercury. Okay, and that is either 76 mercury, 76 centimeter mercury, for example. Okay, and that is because the tool that they use has mercury in it, and depending on the pressure, it could rise or fall. And the weatherman tells you the pressure is rising or falling. We in science, though, we use a Pascal. Because in honor of Mr. Pascal and what he did for this topic in here. Okay, so this is what we use. Pascal is the unit that we use, and it's really Newton per square meter. As a matter of fact, I have to be very careful in here to express it in the fundamental units. So when Pascal is 1 Newton divided by 1 square meter, and 1 Newton is 1 kilogram times a meter divided by second squared, the whole thing divided by 1 meter squared. Cancel the square of the meter with this meter, and it's going to be really a 1 kilogram per meter per second squared. This is really what a Pascal is. Okay, so this is really what the pressure is. Now, knowing that, and because of the weight of the fluid, that is actually another useful property for the fluid, the pressure. The density, symbolically, we use the symbol rho for it. So for the density, and again, we mentioned in the previous units that you really should not be too attached to the symbols. So the density, the symbol for it is rho, sometimes D, okay? These are the symbols used for it, okay? But most of the times, most of the literatures, they use rho, the Greek letter rho. So this is written as R-H-O, the Greek letter rho. And if you don't like that, you can use capital D. Okay, it's the same thing. Okay. The pressure, we use the letter P, usually the lowercase p, but it doesn't matter. Okay, since we only have one P, we don't care about it. Okay, so this is the pressure. So now here is a question. I have this fluid, it doesn't matter. Let's say, for example, water. And I want to know the pressure here at this point. Well, first of all, let me argue that the pressure on any given level below this, this is the level, the highest level of the fluid, is the same at all levels. So the pressure is the same for the entire level below the surface. That means this point in here has the same point as this, the pressure at this point has the same pressure at this point, has the same pressure at this point, the same pressure at this point. You ask me why, I'll tell you why. Take the same fluid, okay? And take a hypothetical, not real, hypothetical, mathematical, okay? Cylinder in the fluid. Put food colorant if you like, and ask yourself, is this fluid moving one way or the other? Obviously, if I do that, and if the fluid in equilibrium, the fluid is not going one way or the other, staying in its place. So in this case, I can tell you the pressure on this side must cancel the pressure on the other side. Why? Because if they don't cancel, the fluid needs to move in one direction or the other, because the pressure is nothing just but the ratio of the force over area. Since I took a small enough area, it doesn't matter how small, it's just a hypothetical, not a real. It's a model. So in this case, the force must be equal to the other force on the other side. And that's why it's not moving in its that's why it's in equilibrium. Otherwise, it needs to move. You see how we went back all the way to the first law of Newton to explain the situation with the fluid? Okay. So that is what helps us understand the pressure is the same for the same level. Okay. It's the first law of thermodynamics. Okay. First law of mechanics. I'm sorry, I'm getting my subjects messed up in here. The first law of Newton. Okay. So that is what allows us to understand that the pressure is the same level. So in other words, if you go below the surface of the swimming pool, for example, 2 meters, it's the same pressure everywhere as long as you are still at 2 meters below the surface. If you go 3 meters below the surface, the pressure probably changes, but it's the same pressure throughout the 3 meters. As a matter of fact, the next question is, how much pressure you have, can you experience if you go further and further down in the liquid? Well, then it must be different. Let me explain. Let me take the same liquid in here and ask the question. If the pressure is P1 in this level and the pressure is P2 in this level, obviously the pressure in P2 must be higher than the pressure in P1 because there is more fluid under P2, which is at depth Y1, and this is at a depth Y2. Since Y2 is clearly more than Y1, that means that there is more fluid on top of it. So I expect the pressure P2 minus the pressure P1 to be a positive number. As a matter of fact, I can tell you what the difference between them is. If I make up a hypothetical cylinder in here of a fluid, the fluid has its own weight, and the weight is the density times the volume. This is an area. This is the difference in height. This is Y2 minus Y1. That's the depth. That's the height of the cylinder. The height times the area is the volume. The volume times the density is the mass. Remember, the mass is just the density times volume from this expression. How we define the density? The mass is just the volume times density. Okay, because the density is mass over volume. So now, if I work out the algebra correctly, that means the mass times G must be equal to the weight of this column of the fluid. So I took a column, hypothetical column in here of a given cross-section A. So the volume in this case is A times the difference in depth. This is just the volume times the density, which I'm going to use the symbol rho or D, doesn't matter. This gives me the mass of this column. The mass times G is the weight. This weight must be equal to the difference in pressure times the area A. The reason why I'm saying that is there is a force from this side, which is just pressure times the area, from underneath, which is P2 times area. And there is a force which is still from this remnant of the fluid, which is this pressure P1 times the area. Again, why do I multiply by the area? Because the force is the area times pressure, because the pressure is force over area. And the second law, or the first law of mechanics, says that these two forces, the net force, you're pushing underneath with a force and you're pushing on top of the force with another force. This two must be equal to the weight to keep it in place. Otherwise, the entire fluid will sit in the bottom. The entire fluid, if this is not true, will sit in the bottom. Since each column must be compensated by the difference in pressure, this must be then true, that this is equal to the pressure from the top and the pressure from the bottom times the pressure from minus the pressure times the area A. Obviously, I took an arbitrary shape. It's not real. This cylinder is not real, doesn't exist, and its properties should not matter. So I took a cross-section A, which needs to cancel this cross-section A, And the difference in pressure now matters. The difference in pressure depends on the depth that we're in. So it's the density of the fluid. So this depends on the fluid times G, which is 9.8 meter per second squared, meter per second squared. This is the gravity times the difference in depth. So this is important. This is a useful formula, by the way. It's going to help us do a lot of calculations. So the deeper you go in water, that means the bigger Y2 is, the more pressure P2 is going to be. This is a key concept that we need to understand. So if I go back into a liquid, I was able to describe its properties. Now we know its density, we know its pressure, because if I make Y1 equal to 0, this is the mark where Y1 is equal to 0, then the pressure at any given depth, P, is actually just rho times G times Y, where Y is the depth. G is just a fixed number, it doesn't change. And rho, it depends on the fluid. Rho for oil is different than rho for the water. So now this is we have quantified this problem. Okay, I know the book probably has a different explanation for it, but I'm giving you actually a different view of it so that you guys can see what these properties are. So let me go back into the notes from this week's what we're supposed to learn here. Let me stop sharing the screen and share with you the screen. Okay. So can anybody remind me of the discussion item today?
To do the review.
Very good. Yes, I'm going to remind you about that. The second item today is the two key properties of a fluid are density and pressure. Sounds good. The two important properties, pressure and density. Okay, so from now on, we can describe things. So do I have my share screen showing the week 5 objectives? Yes or no? I want
Yes.
confirmation. Very good. Thank you very much. Okay, so basically, these are the two concepts that we have discovered so far. The buoyancy in a liquid is that exactly the same thing. An object that is submerged inside the fluid. Because from underneath there is a bigger pressure from the top than the top, then it feels itself being pushed upward. Okay. It feels the difference in pressure. And the difference in pressure, there is more pressure. Depending, of course, on how big the object is, the more pressure from underneath, less pressure from the top, and that's why the objects are coming up in this case. Okay. Archimedes' principle says the following. The difference, the buoyant force itself must be equal to the weight of the displaced liquid. This is an interesting experiment. Actually, I think I included the video for it there so that you can see that indeed it is true. And if we are in a classroom, we can demo this one, okay, that the weight of the displaced liquid is the one that is equal to the buoyant force. So here is a trick. If I take a lump of iron, it doesn't matter how big it is. And if I make it into a lump and put it in any water, including the ocean, it's going to sink. Why? Because the density of the iron is much higher than that of the water, so it's going to sink. Okay. If I take a piece of wood, for example, and put it on the surface of water, it doesn't matter how much water it is, as long as it has a little bit of depth, it's going to partially submerge and partially stay up, and it's going to be it's going to float. Okay. How much goes in, depending on how much wood you have, and it's going to displace just enough so that if there is very little depth of water, so that's going to at least touch the surface. Okay. Again, it has to do with the density of the wood in this case, which is a fraction of that of the water. So how can you make a boat float? As long as you displace more fluid or at least enough fluid that cancels its own weight, it's going to float. Let me explain this point in here. Very important. We share the same screen I was earlier with. Share. So I have a boat in here, made out of steel. That's what boats are made out of. So steel is iron for the main part, with a little bit of doping from carbon and other materials to make it more resistant to other properties. So you have iron basically, okay? And if you take an iron and put it in a regular shape, it doesn't matter, and you put it in any surface, including the entire ocean, is going to sink to the floor, touch the ground, okay? No question about it. But what you can do, make it into a bigger volume so that it displaces more water, so it's going to stay float. So this is a cross cut from it. So this is what you do in this case. Take it like this. It's the same amount of steel that make it into this shape and put it on the surface of water. So the water before you put it was at this level. Now, because of this entire volume, this much, okay? The water has rose to this level. And the buoyant force, which is the weight of the displaced fluid, this is the weight of this much object. As long as this buoyant force is equal to the weight of the boat, the boat will float, will not sink. Of course, this is a cut from it, okay? Cross-section cut from it, okay? The boat is a long object, so I'm just showing you just a cut from the ocean as much as I'm showing it in here. Obviously, the ocean is so big. With a single boat or even 24 of them, you're not going to see any kind of change in the volume. You hardly are going to measure any kind of change in volume. But it is there nonetheless, and that's what keeps the iron to stay on the top of the surface of the fluid. So again, this is an idea that is very important. The story says is that Mr. Archimedes was basically taking his bath, was in a bathtub, basically taking his shower, taking his bath, and then he figured it out, why he can float and how much force he can float with. So he came out running from his bathtub, screaming, "Eureka, Eureka, Eureka, I found it, I found it, I found it." What did you find? He told them about the principle, okay? That the displaced fluid is the one that cancels the force of the weight of the object. Okay. So as long as we have that, that is a critical piece of the puzzle. So let me share again the objectives for today. Again, gas has pressure because gas, albeit it's a liquid actually too, a fluid I should say, not a liquid. And it also has the same properties, and you can measure pressure, and the concept of atmospheric pressure is coming from there. And it's similar, it has density also, except the atmospheric pressure, 101,000 Pascal, looks like it's a big number. It's just a column of air. If you stuff it correctly, and if the gravity does not change, it's about 10 kilometers. It's not really that high, okay? Obviously, the atmosphere extends far more because the density changes, okay? Hundreds of kilometers probably, never ends really, but it becomes so small that it becomes insignificant at some points in here. I mentioned the atmospheric pressure, which is 1 atm, atmospheric pressure, which is 101,000 Pascal, which begs another question. How deep can I go under the surface of the water for me to be able to experience another atmospheric pressure to the first one? Let me explain the numbers and how we get it, okay? Because it's an interesting question. Share, same screen I was in, share. So let me explain this question because it's a common question that comes all the time. So you have surface of the water. At this point, you have 1 atmospheric pressure already pushing on the ground. And you would want to go depth under the surface of water to experience another atmospheric pressure. So the difference in pressure is 1 atmospheric pressure, which is 101,000 Pascal. I'm going to roughly write it as 100,000 Pascal. So this is the difference pressure must be equal to the density of the air. The density of the air practically is 1 kilogram. That's another number to remember, okay? So remember, the density of water is 1,000 kilograms per cubic meter, or 1 kilogram per liter. For air, it's 1 kilogram per cubic meter. It's 1,000 times, it's slightly more than 1, actually. It's 1.29, but that's like a rough number, okay? I'm just using a number in it. So it's 1, actually. So the density times G is 9.8, which is roughly 10. I'm just getting an estimate in here, equals to Y. Okay. Oh, no, I'm not using the air. I'm sorry. I'm in the ocean. I'm in the water. So under the water, it's 1,000. I have to use this number. I'm not going in the air. I'm going under the water. So I have to use the density of water, which is 1,000. So I have to be careful in here. Obviously, 1,000 times 10, that's 10,000 times Y. So in other words, how deep I need to go? Divide 100,000 by 10,000. The answer is 10 meters. So Y is 10 meters. So if I go under the water for 10 meters, I experience an atmospheric pressure. If I go 100 meters under the surface of the water, I experience 10 times the atmospheric pressure. So if this is the ocean, and this is 10 meters, so this is 10 meters, I need to go 100 times, which is at 100 meters deep. Then in this case, I experience 10 times the atmospheric pressure. This is too much of pressure. It's crushing pressure, by the way. 100 meters without the proper equipment, you will be crushed inside. You will implode. It's not good. Okay, so you need to have a proper equipment to go that deep. I'm not talking about breathing. I'm just talking about pressure. That's all. If you go kilometer, then you're talking 100 times that number. You really have to have a proper submarine to go that deep, 3,000 feet under the ocean. It requires a lot of proper machinery. Otherwise, you cannot survive that much pressure. 100 times atmospheric pressure requires steel and all kinds of enclosures to be safe. Now, the deepest ocean is about 11 kilometers. So we're going to go about 10 kilometers. And at that point, you're looking at 1,000 times atmospheric pressure. It is really hard to get into that deep because of the atmospheric pressure. The question for you is, there is squid in this area and fish and all kinds of submarine life in there. How do they manage to survive that much pressure? 1,000 atmospheric pressure? What do you guys think? Are they made out of super strong steel? That fish? Or squid? Or other living organisms in there? What do you guys think? Any suggestion is fine. Okay, let's make this one as item 3 of the discussion then. And this, you really need to research it. You need to find out, how does the fish survive the deep depth of the oceans without being crushed by the sheer amount of the surface, by the sheer amount of the pressure. They are not imploded. So I guess item 3 of the discussion now. That is actually a research question. You guys need to go and find out and let me know. Okay. Do you already understand the question or not? Please, the ones who are here.
Yes.
Okay, very good. Let me type it for you guys so that you can
Professor,
find it.
do we have to provide a link for the information that we found?
You don't have to provide the link. All you have to tell me is what is the secret of the fish.
Okay.
Okay, because I want to know that, so that if in case we're stuck in there, so that we can probably use the same trick. Okay. So question is, how does the fish survive high, or I'm going to express it. I want to use a number, but I don't want deep ocean pressures. Remember, it could be in the thousands of atmospheric pressure. I mean, if you want to crush something, you usually just use very little surface and it crushes. Okay, that's not even probably that much pressure at all. 10 atmospheric pressure will crush you, will basically you'll implode, you will flatten with it. 100 atmospheric pressures, you're going to be squeezed like nothing. 1,000 of it. So what is the secret of this living creatures? I mean, what do? Do they have shells made out of super strong steel that maybe we need to use to protect our cities from all kinds of disasters and fires and asteroids and things like that hit us? Maybe you can use the same trick if somehow we can learn from what they do. Or maybe it's a lot simpler than that. Okay. So that's item 3. So I really want you guys to think about this one and put it as item 3 of the discussion. Let me see what left in here. Okay, Bernoulli's principle now is another important aspect in here, and let me explain that, and that's we're getting close to from the end. So share and here is the trick with this one. So up to this point, we were describing fluids that are not moving. This is called branch of physics called hydrostatics. Hydrostatics means that liquids don't move. You put a column in there, a food column, for example, and the water is not going anywhere. Now, there is another type of fluid dynamics that we study, and it's called hydrodynamics, actually. And that is how fluids move from point to point. I mean, if you ever go to the faucet and open the faucet, water comes in rushing from it. Of course, this goes through a pipeline, it goes through a conduit before coming in there. So it's flowing. As a matter of fact, it's of interest to us, for example, when it comes to taking like petroleum, for example, from one location to the location and using pipelines. It's of interest to us, for example, when it comes to the flow of air, which is a fluid also. So that's important, especially if you're going to fly in the air. So you want to understand it, okay? Whether weather related or technology and things like that. So we really need to understand the flow. There are 2 types of flow. There is the so-called laminar flow, and there is the turbulent flow. The turbulent flow is a little bit outside of the scope, and this is like, for example, a tornado, okay? The motion is more or less unpredictable. So we call it a chaotic motion. But even a chaotic motion will have some sort of an order in it, some sort of guidelines in it. And that is of a different topic that we're not going to have. So in other words, there's a clear distinction between that one and, for example, where the flow is all. So if you can think of the fluid as made up of different layers, those layers are moving in the same direction with the same speed. This is the laminar flow. So it's a layered structure where each layer, each two adjacent layers, they're moving in the same direction. So this is a nice, smooth, linear flow, which is easier to understand. So the laminar flow is kind of easier, it's linear, whereas the second one is non-linear and it's usually involves all kinds of math to get into it. So for the laminar flow, there is a law that governs it, and the law is that of Bernoulli, and it's basically the following. The energy is conserved. That's basically what it is. So the energy is the kinetic energy, of course, but I'm using it in per unit area. So this is joules per meter squared, okay? So it's an energy density, not really an energy, okay? This is the kinetic energy plus the potential energy. Again, I usually have the density times the volume, and the volume is area times height. That gives me the mass times G. Am I missing another term in here? Or GH, that's correct, okay? Let me make sure the units are correct, okay? Kilogram per meter cubed times meter per second squared times meter. And if I have another meter squared in here, so I have the meter cubed and the meter and the meter, and so I'll have Newton in here only. Am I missing a term in here? I need to verify this thing in here. This one is a kilogram per meter cubed times meter squared per second squared. The units match. The units match. So the units match, okay? So it's not really a unit energy density, okay? But it's actually derived from the energy density. There is a missing term in here, but it's still the same thing. We talked about the energy, the total energy, plus the pressure is equal to constant. So this better be pressure now. Kilogram meter. So this is a pressure, okay? The proper units. So a kilogram meter, meter squared. So if I look up in there, so the units that I'm looking at is a kilogram per meter second squared. Is this the same unit that I have up there for the pressure? Remember, I expressed the pressure in terms of the fundamental units. And it's sure enough, 1 Pascal is 1 kilogram per meter per second squared. So it really expresses the pressure imbalance, and the pressure imbalance is actually derived from the energy. So this is actually, everything is in Pascal. Everything is in pressure, but it's derived from the conservation of energy. This law is that of Bernoulli. That we call this one Bernoulli. So again, let me rewrite it cleanly. It's constant, does not change. This is coming from the kinetic energy. This is coming from the potential energy, the gravitational potential energy, and this is coming from the work of external forces. If you take an element of a conduit, for example, here is a conduit. It has an opening in here, and it has a different opening, not necessarily the same length in here. So the area in this case is A1, the area on the other side is A2, and the fluid is at a different heights. So this is H1, this is H2. So in this case, the height in here, that's where the H is. So the potential, there is a gain in potential energy. There is a difference in pressure in here. So there is a pressure from this side, and there is a pressure from this side, and the difference in pressures is P. So in other words, this quantity on the top must be equal to the quantity on the bottom, and that is where this quantity is coming from. So this is Bernoulli's law. Bernoulli's expression is very, very important because it helps us understand a lot of things. One of them is the liftoff of a wing of a plane, or the plane in general. So if I have a plane wing that has this shape, the flow of the air as the wing is taking off, as the plane is taking off, is laminar, at least in the first approximation. So what I can say in here is, let's say, for example, I have this point in the flow, this point in the air, before the plane reaches it, the air, I mean, from the vantage point of somebody sitting in the plane, the air is rushing to us. Yes, the plane is moving, but I'm sitting in the plane. I'm not moving. So the plane, as far as I'm concerned, the air is coming to meet me. So the air that is going underneath is undisturbed, basically, because it's below the wing. The air that is the portion, or the laminar portion that is immediately above, is going to be cut by the wing, and has to go above the wing and come down again, and must stay in the same condition as the other one started, because it's a laminar flow. So here is the problem. The path taken by this portion of the air must be longer than the path of this portion of the air that is below the wing. Because they start at the same point and they stay in the same point as their lane passes by, then in this case, the air in the top must travel at a higher velocity. So the velocity on the top for the laminar portion must be higher than the one below the wing. So this is only the wing. Okay. Since the velocity is higher, the difference in height is negligible, so I'm not going to include that. So that means the pressure on the top plus 1/2 the density of the air times the velocity squared on the top must be equal to the pressure in the bottom plus 1/2 the density of the air times the velocity in the bottom squared. This velocity in the bottom or below is less than this velocity, so this pressure must be higher to compensate for it. In other words, I can take this equation and solve for the pressure from the bottom minus the pressure from the top. So in other words, I take this number and move it to the other side, it becomes negative. And take this number and move it to the other side, it's going to be negative. So this must be equal to 1/2 the density of the air times the velocity on the top minus the velocity on the bottom squared, of course. And this is a positive number because the top is higher than the below. So this is a positive number. That means the pressure from the bottom is higher than the pressure from the top. The pressure from the bottom is higher from the pressure of the air from the top. And that's what causes the plane to lift off. Because there is more pressure from underneath, from the air underneath. That's what causes the plane to take off. Okay? So we have an understanding now of where this thing is coming from. It's really the difference in pressure, and that is what causes the liftoff. Obviously, if this thing is moving faster, there is an imbalance because the faster, that means this one has to be coming in here faster, and this one stays the same. This does not change. This is the calm air. It's this one that must cross the entire thing faster than this one. So then in this case, the imbalance, the difference in pressure would be higher, in which case will cause the plane to go higher. If it's going very slow, then the difference in pressure would be unnoticeable. The difference in velocities will be unnoticeable. Hence, the difference in pressure will be unnoticeable, and the plane does not get to take off. Okay? It won't take off because of the fact that you don't have enough difference in pressure. You don't have enough liftoff. So the liftoff is actually coming from the imbalance in the pressure in the wing. If you take the wing and reverse it, put it like this, and put it in a car, in a NASCAR cars, again, the same thing is happening in here. There is higher pressure in here and there is less pressure underneath to compensate for the air. So the pressure will be higher in here than the pressure from underneath the wing, and that's what keeps the NASCARs from flying. They use actually this reverse wing so that they stay on the track. Otherwise, they will fly. Okay. Do all of these things make sense to you guys? Yes, maybe. I would recommend you read the book. Okay. If you have any questions, please let me know. There is another typical example at this point, and the example has to do with a sink ball when you're playing baseball. Again, you give it a spin, and that ball will go spinning And at some point, the portion on top is going down in the same direction with the ball, which means that it's going at a higher speed than the one below. Okay, that too will cause actually a drop in the ball. Okay, and that is how you explain a lot of this phenomenon. Okay. So these are the concepts covered through this week. These are the stuff that is important. The main thing this week, am I still sharing? I think I'm not sharing anymore, okay? The main thing is a review for the exam and the exam itself. This unit is important. And hopefully, guys, you still have time to respond to the question. It's still not due until after the exam. And the question is simple enough. First of all, the item 1, remember, is do the review. Item 2, the 2 main properties of fluids are pressure and density. And item 3 is this one, which is an interesting question, is how does this fish survive? What is the secret of the fish not to implode under those tremendous pressures in the ocean? Okay. So this is in a nutshell. If you have difficulty with the last part, basically say I couldn't find it or anything like that, but it's not supposed to be, it's not an exam, by the way. You're not supposed to, I mean, if you don't find the correct answer, there is no penalty for it. That's my point, okay? You don't find the correct answer for it, it's not, there is no penalty for it, but it's an interesting one because you get this fish that sounds kind of, you can squeeze it with your own hand. And you take a fish and you can basically damage it if you're not careful with it. Yet it survives as much higher pressures under the oceans, even the ones that are about 100 meters, the ones that we have them in a day-to-day, basically in here. You don't have to have a squid or any of those deep ocean living creatures, and they still survive tremendous pressures that we cannot survive, but they do. Okay, so this is the introduction for this week. Hopefully you guys will take the review and then start working on this unit because it's going to be important for the next exam too, in this chapter. Sounds good, everybody?
Yes.
Okay, very good. So I'll see you guys. If you have any questions, please let me know. I'll be more than happy to meet on a one-to-one basis, depending, of course, on the schedule. And I'll see you for the next unit. And then if there is a problem with the exam, please let me know. Hopefully some of you will take it right away on Thursday. Do not wait until the last days. The last day is when your internet stopped working. That's the day when typically problems happen. There is a problem with the internet. There is a problem with the electricity. There is a problem with something in there. You're out of time. So do not do that. I mean, typically, you should really think of worst case scenario. Sunday is when I do my exam. There is a power outage. There is a problem with the weather. Probably there is a Canvas issue. And sometimes these things happen where the IT sends us a message saying, hey, Canvas is not available for the next, I don't know, 3 hours, 4 hours or something. And you were relying on that. Now you don't have access to it. So that's not really an excuse. The thing with it is, since it's open on Thursday, take advantage of it right away. Put it behind you, okay? If you cannot do it on Thursday because of other classes or something else, or you would want to sit down and review the materials, that is your prerogative. Try it on Friday. Friday you're busy, there is a family thing and whatever. Do not leave it unless you really, there is something. Saturday is your day. Somebody asks you, let's go and hang out, or let's do something, or family get it. No, I have an exam. I have to take my exam. It's important for my class. Delay those things. The exam is not long enough for you to lose the entire day. So that is the day when you do this thing. You delayed it further until Sunday. Now you really, it's an urgency in here. The point I'm trying to say is do not come Monday at 9:25 p.m. and decide, you know what, where is Canvas? I don't find the link, or the link is not working, or start to panic at that point. That's too late. Again, I will try to send you reminders, and hopefully you're on top of it, everybody. Thank you, guys. Let me stop the recording first.